Hello. These are your notes for today, so make sure you have them. It's just front and a back. There's no staple on them. So today's our first day of this like little mini unit at the end of the year. The nice thing about these 3 days that we are spending is that they will also help you review for the exam. So remember, your exam covers all of the second semester. So knowing the difference between these function types will help you on the exam, and also it will help you in future math classes. So it's just a really good thing to know. So we will take notes on this, and then you'll have homework with this as well. So first, I think we all hopefully know this. The shape of a linear function is a line. So what we're doing here is we are drawing two different lines. So here it says when, actually I'm going to write the equation up here first. The equation for a linear function, I'm going to write slope-intercept form. Remember, we also did point-slope form as well and standard form. But slope-intercept is probably the most common. So when m, which is the slope, is more than 0, we're just going to draw a line that has a positive slope. So anything that's like going up. So that line would have a positive slope. When the slope is negative, the line looks more like this. And I'm not concerned with the y-intercept here. You can put it wherever you want, but we're just talking about slope in this top little section. The next kind of function is quadratic. We just spent a lot of time on quadratic functions. I'm going to write the standard form of a quadratic function here. So that ax squared plus bx plus c. And on this part of the notes, we're just focusing on what the a value does to the graph. So remember, the a value controls the direction of opening of the parabola, like whether it's up or down. It also does control like vertical stretches and compressions, so it can make the parabola wide or narrow. But here all we're talking about is just the direction of opening. So when a is more than 0, it opens up. Doesn't really matter where you draw it on the coordinate plane, it just needs to open up. And then when a is less than 0, it opens down. And then the final function type we're discussing here is exponential. So when we have an exponential function, this like standard form of an exponential function is y equals a times b to the x. Remember, the thing that makes that an exponential function is the fact that the x is in the exponent. That makes it an exponential function. So what we're doing here is just like kind of showing the difference between growth and decay. So when the base, remember this a value is the y-intercept, b is the base. When the base is bigger than 1, it's growth. So draw an exponential curve going up. And then when the base is between 0 and 1, it's decay. So we should see a curve going downward. Those are kind of some weird arrows, but remember, it's not going to cross that x-axis. So here we're kind of just looking at these equation types and differentiating between the types based on how the equation looks. So keep in mind, the key to this really is all up here, this thing that I'm about to highlight in yellow. We're using those ideas. So linear versus quadratic versus exponential. So this first one looks like a linear function. Specifically, it's a linear function in slope-intercept form. We can just write linear. The directions are to classify the function. This next one is exponential because we see a variable in the exponent, and it wants us to like show like whether it's exponential growth or decay. This is exponential. I'm going to abbreviate exponential because this box is small. Growth, because the base of the exponent, the thing directly to the bottom of it, is more than 1. So that would be growth. This next one is a quadratic function. We just did a lot with those in our last unit. This is a quadratic function in standard form. This squared makes it quadratic on the x. Okay, this next row here, this is exponential. It's exponential decay because this base is less than 1. So exponential decay. The next one happens to be a quadratic function. It's not in standard form, so it might be a little bit harder to recognize, but if you were to multiply this all out, x times x is x squared. So it has that x squared in it, which makes it quadratic. It happens to be in factored form, but it's quadratic. You don't have to get it in standard form, but you do need to recognize it's quadratic. The next one is a linear function. It's kind of in y equals mx plus b, but just kind of backwards form. So that's linear. Oops, I lost my R. Okay, the next row here, this first one is definitely exponential. I see that x in the exponent. The thing directly to the base of the exponent, so by that I'm talking about this 3/2 right here, that is bigger than 1, so that would make this exponential growth. The next one is y equals 6. That's a linear function. We actually referred to it as a constant function earlier this year. It's a horizontal line, it's constant. That's not really a choice here, so it is a linear function if it's a horizontal line. This next one has an x squared in it. Again, it happens to be in that like factored form, but it's quadratic. All right, and then this final row, this number 10 is a little tricky to recognize, but if you were to solve that for y, because you want your function to be y equals, you'd want to get rid of that divided by x. So you want to multiply both sides by x. It's kind of hard to write that there on top of the 10. But over here, you'd want to multiply by x as well. So like on the left side, those would cancel. You'd have y equals x times x plus 1. I'm just going to write the x in front. If you were to distribute that x times x is x squared. So because of the presence of that x squared, it's definitely a quadratic function. I do not have a lot of room here, but I'm going to squeeze it in. So that one's quadratic because of the x squared. The next one is 1/2 times 6 to the x. I see the x in the exponent. When there's a variable up here, it's exponential. It's exponential growth because the base of the exponent, because the base of the exponent is 6, it's bigger than 1, which makes it exponential growth. This last one is a linear function. It's not solved for y. You don't have to solve it for y. That is what we call standard form of a linear function. So that one's linear. Okay, so the next part of the notes, we are just looking at like the shape of the graph as opposed to the equation. So we're looking at the shape of the graph and saying what type of function it is. So this first one, and the key to this is like up here on your notes. I'm going to highlight it in green. All of this is the key to this next section that we're doing. So just go based on the shape of the graph. So this one is exponential. It's a classic exponential function. It's exponential growth. It's going up. Remember, as we get towards exam review, we'll talk about this more, but this x-axis is what we call an asymptote. It's a line that the graph approaches, but it's not going to cross it. This next function is linear. It's a straight line, so it's definitely linear. And then the last one on this page, that's a parabola, which means it's a quadratic function. Then here we have another function type. This actually is a cubic function. You'll learn more about how they look like in Algebra 2, but it's none of the function types that we talked about. So none of the above was a choice, so I'm just going to say none. This next one is linear. And then this final one is an exponential curve again. Notice it did cross the asymptote, like the x-axis, it crossed it, it's below it. It must have had a vertical shift, like it must have translated down. We will review all of that with the exam review. So this is exponential decay, it's going down. And the final concept on your notes is just talking about how to differentiate between these function types based on tables. So this first table here is showing a linear function. And as we talked about earlier this year, for linear functions, there's a common first difference. So that means the differences between these y values are consistent the whole time. So it looks like in this table we're subtracting 1 every single time. So that makes a linear function. Quadratic has a common second difference. So this is a little bit harder to see. So what you're going to do is you're going to look at the y values and you're going to find their differences. From -3 to 5 is up 8. If you have a hard time doing that math in your head, you just take one number minus the one before it in the calculator. So like in the calculator, to find this difference, you would type 5 minus -3, which is actually 5 plus 3, which is 8. So the first difference there is 8. it goes up 8. So this, I'm just going to say 8. Then it goes from 5 to 9, that's up 4. Again, if you have a hard time telling, you can always take 9 minus 5 in the calculator. 9 to 9 is 0. 9 to 5 is down 4. Those are definitely not the same, so it's not linear. Then you find the differences of the differences. So from 8 to 4 is down 4. From 4 to 0 is down 4. From 0 to negative 4 is also down 4. These are the second differences, and those are all constant, which makes it quadratic. These are the first differences. Exponential, there's a common ratio. We talked about this quite a bit, which means you're going to be multiplying. So 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. So that is exponential. Oops, I did not mean to cross that off. So common ratio for those. So down here, we're just saying, is it linear, quadratic, exponential, growth, decay, or none of the above? So this first one, we want to look at the y values. It looks like we're subtracting 2 every time. Again, if you have a hard time telling that in the calculator, you can just take one value minus the one before it. So for example, negative 6 minus negative 4 is going to be negative 6 plus 4, which is negative 2. But if you can look at that table and tell you're subtracting 2, that's good. So here we have minus 2, minus 2, minus 2. Consistently subtracting 2 means it's a linear table. So that first one is linear. The next one, 135 to 45 is down quite a bit. That's down a lot, like 90. From 45 to 15, it's not down the same. So it's not linear because it doesn't have a constant rate of change. To see if it's exponential, we can see if there's a common ratio. If you can't tell, you're definitely not like multiplying by something, you're dividing by something, which is the same as multiplying by the reciprocal. But if you want to see if it's exponential, what you actually do is you can take any term, like any y value, divided by the y value before it. If all 3 of those are the same, so if I do the same thing for the next one, 15 divided by 45, if that's the same as 5 divided by 15, then it's exponential. Those are all the same. They all simplify to 1/3. So this is exponential, but it's exponential decay because the numbers are going down. Okay, this one looks like it's not linear. We are not going up the same amount every time. Let's look at those first differences. So we're going up 30. Then we're going up 59 minus 25 is 34. Then we're going up 97 minus 59 is 38. Those are not the same, so it's not linear. Look at the differences of those. From 30 to 34 is up 4. From 34 to 38 is up 4. These are called the second differences. When the second differences are the same, it's quadratic. So this is quadratic. This next one, when we look at the y values, it looks like we're multiplying by 4. So, and they're getting bigger, so it's exponential growth. Remember, if you want to check for exponential, you can just take every y value divided by the one before it. Should be the same for this whole chart. All of those are going to be 4. So it's exponential growth. You don't necessarily need to show that work, you don't need to show those equal fractions, but it's going to be exponential growth. This one, negative 16 to negative 9 is up 7. Negative 9 to negative 2 is also up 7. Up 7. Those are the first differences, and they're the same, so that's linear. This one, 14 to 26 is up 12. 26 to 44, if you do 44 minus 26 on the calculator, that's up 18. 44 to 68 is up 24. Those are not the same, so it's not linear. But if you look at these, from 12 to 18, that's up 6. From 18 to 24 is up 6. So the first set of differences is not the same, so it's not linear. The second set of differences is the same, so this one's quadratic. All right, so that is it for today's lesson. The sub is going to pass out the homework now. It looks a lot like your notes, so you're going to work on this homework for the rest of class. I will see you tomorrow.